the other sessions, and I'd like to welcome you to my talk on memory, garbage collecting, G1, pauses, latencies, and so on. Well, my name is Jaromir Hamala, and I work at the company called C2B2, and my official title is a senior consultant, which I don't like this title much because I don't consider, okay, 1, 2, 3, okay, that's better. I don't consider myself as a consultant. I consider myself more to be like a curious developer. That's what I like to call myself. Can you hear me? Yeah, great. So I like to consider myself as a curious developer who is curious about a lot of things. So not just about computers, but well, mostly about computers. So I'm not curious only about, let's say, Java or software. I'm curious about hardware. So I am curious about processors, about how JVM works inside, and well, I'm curious also about new languages and lots of other things. I like to explore the world, and I like a beer. Well, and given that I'm from Czech Republic, that I was born and raised, I like a beer, and Devox is in Belgium. It's quite obvious why I'm here. Well, agenda for the talk. Well, we will start from the very beginning. We will talk a little bit about memory management in general. We will see, or I will show you different garbage collectors in JVM we have. Well, most of you probably know this. We will compare a bit CMS against G1 garbage collector. I will show you a little bit about the tuning of G1, and we will end up with some set of recommendations where to use, what is a good use case for G1, and well, what is probably not a good use case, or when is not a good idea to use G1. Well, I promise that we will start from the very beginning. So, I guess most, if not all of you, are or used to be a Java developers. So, this will be a little bit, at lower level than you are used to work. But, well, the news is that the good old times where all the memory in the computer used to be yours, these times are over. When in the past you used to be a king of the hardware, all the memory was yours and you didn't need to ask for permission to use memory. Well, of course this is depending on architecture, but this is the idea. But these times are over. Now you are not the only one who is, your process is not the only one who is running at the hardware. So your process is competing with other processes about the memory. Memory is a shared resource, and therefore, before you can use some memory, I mean the physical memory, you need to ask for it. And so in a C, if you know a C, in the standard library of C is a function called malloc, memory allocate. So in C, when you want to use memory, you will call this function. This function will eventually ask for the memory to the kernel of operating system as break. And well, if your process is a good process, well, the operating system will decide to grant you more memory. So you need to ask before you can start the memory. And in languages like C, of course, when you no longer need the memory, you need to release it because, well, the operating system, neither the standard library, cannot know that you no longer need this memory, so you explicitly need to to release it. Well, sounds easy. Sounds easy, and the first step usually is easy. Well, you want the memory, you will ask operating system for memory. Asking is easy, we know it. I can ask my colleague Nick, who is sitting here, for money, and I can ask him, and he might give me, and well, I will use the money, and I will promise that when I no longer need the money, I will return it. Well, eventually, because I'm a greedy bastard, I will not return him this money, and well, Nick will never have this money again, and that's exactly what's happening if your process is asking for memory and never release the memory. The operating system will not have an access to this part of the memory again, and even if you don't use it, well, still bad luck. So the second part, the returning, is more complicated, so it's same as in life. Well, we have a guy to rescue us, good guy, garbage collector. So the clever guys back in end of the 50s were thinking, how can I improve it? How we can improve this? It's very prone to errors. If the process is bastard, with bugs, with errors, and he will not return the money, the memory. We will end up, without resources, without memory, and we will need to start killing processes. So we want to automate the process of returning or reclaiming the memory, and that's exactly the role of a garbage collector. When I was looking a little bit, about the history of garbage collectors, so of course I use Google, and the first page, was about some old grease and garbage and so on. So we can see that the garbage is not a new concern, that even people in old Greece were concerning about the garbage and how to deal with garbage. Well, as I said, the idea of having a memory to be automatically reclaimed came from end of 50s, from the area of Lisp. And good news for us is that in Java we have automatic garbage collector since very first version. So in theory, we shouldn't care about collecting the garbage at all. And later we will see that it's not 100% true, but well, it's close. So now we know that garbage collector is that good guy who is reclaiming the memory we don't use. And now we are in the position of a customer of JVM, and we can make a list of requirements. So we are a customer, and what we want from the JVM, what we want from the garbage collector. Well, we want, of course, a garbage collector to have a high throughput. What does it mean, high throughput? It means that we want to spend as little of our expensive CPU cycles doing garbage collecting as possible. Because if CPU is doing garbage collecting, well, it's not running, or it's not running our application. So more cycles in GC means less cycles for us. So of course we want high throughput. We also want low latency. It means that the existence of or presence of garbage collecting or automatic reclaiming of memory should not have an impact on response time or responsibility of our application. So no impact, or as little impact as possible. And of course, we want that garbage collector to have a minimal memory footprint. So, well, of course, to implement a garbage collecting or automatic memory reclaiming, we need to maintain some additional data structures and so on, and it costs us a memory and a CPU and so on. And we want this footprint to have as little as possible. And of course, this goes without saying. We want a garbage collector to be reliable. And well, it would be nice to have a feature or requirements from us as a customer of JVM is to have a garbage collector which will be easy to use or tune. So if we have some issues related to the throughput, latency, and so on, we want to have an easy way how to fix these issues. So if you think about it, we are like a typical customer. We want everything. And well, of course, there is no free lunch, and as often some of these requirements are going against each other, so we are forced to do trade-offs as usual. So before we look at the ways or at the list of garbage collector implementations we have in JVM, there is very little bit of the theory which is worth to know. I guess most of you here know this, but anyway, there is this thing called generation hypothesis, and it says that most of the objects die young. That's a very important hypothesis, and most of the garbage collectors are based on these assumptions. It means, and you know it from your own coding, that really most of your objects you allocate, on the heap, well, you allocate the object, you will use it, and well, you will throw it away, and you no longer use it. And this is really vast majority of objects in the typical applications have this characteristic. So we can use this to our advantage. And there is another important assumption is that objects which happens to be old, it means they didn't die young, well, they tend to not reference the young objects very often. It means that, well, we will create a new object, and our new object might reference the old object, but it's very rarely vice versa. So that's another assumption or hypothesis we can use to our advantage when we are designing a garbage collector. So we know the hypothesis, how to use it. Well, the obvious thing to do is to split the heap. Well, we can say this is my old heap, and I will split it. So the part of the heap, some area will be considered as a young, and so it will be the area where the new objects will be allocated, and the other area I will call it old area, and well, if objects will not die, this object, well, I will move it to old. And what's important that I can garbage collect these two areas separately using different algorithms and also using different implementations. So that's the idea. Split the heap. That's the important here. And another little bit of theory, we should know the meaning of these three words: concurrent, parallel, compacting, because these are the three main characteristics of garbage collectors. We'll start with a concurrent. What does it mean, concurrent GC? And I would stress the difference between concurrent and parallel, because, well, it sounds very similar, but it's something completely different. So concurrent GC, if we say that the GC is concurrent, it means that it is able to do a collecting concurrently with our application. So this, I have examples of two implementation of garbage collectors. The left one, this one, is a concurrent. It means that, well, here the time is going from up to down here. So here we have 4 threads, and all 4 threads are running our application code. So now here at this time start the GC cycle. And, well, 3 threads are still running our application code, but 1 thread is running GC. The important here is, well, it's running concurrently. So our application is still doing something. Well, maybe it's doing less because it's running on less cores, but, well, it's still working. If GC is not a concurrent, it means that once GC kicks in, our application is not doing anything. That's very important, because, well, if our application is not doing anything, well, it's not providing any results, it's not responsive, and so on. So this is the concurrency. The second term was parallel. What is parallel GC? As I said, is very different from concurrency. The terms, it's not either parallel or concurrent. The terms are orthogonal. So GC can be parallel and concurrent. It can be parallel and not concurrent, and so on. So the terms are orthogonal. Parallel means that to do that GC use multiple threads to do work. So again, we have two implementation of garbage collectors. The left one is parallel. It means here where my application was running here. GC kicks in here, and, well, the GC was doing work. 4 threads were doing the GC work, and once they finish, well, my application was running. The right one is not parallel. It means that only 1 thread of GC was actually doing the work. It means, well, to do same amount of the work, but by using only 1 thread, well, it will probably take a longer time, and it's true. So that's the parallel GC. Well, what does it mean? More threads. Well, the third term, was compacting GC, and instead of explaining what does it mean, compacting, I will show you what will happen when GC is not compacting. So now imagine this is the heap, and we have 3 snapshots of the heap in time. Now I don't take this division between young and old generation into consideration. It's not important. So this is our heap, and, well, it looks pretty full. There are some objects, and, well, most likely we would like to reclaim some areas to be able to use it for new objects. somehow using some algorithm. That's not important for now what the algorithm is. The important is that the garbage collector will find the objects which are used and will let's say mark it somehow. And well, now we know which objects are being used, so we can reclaim the address. So what garbage collector will do, it will say, well, this object is not used, so well, there is a free space, and so on and so forth. So you will end up with this. The only objects which were marked as a living object will stay in the heap, and the others will be reclaimed, and the memory will be marked as free to use. Important is that the objects which were marked as used, well, they will not be moved, they will stay in place. So the result of this will be, it will be look like this. There will be fragmentation. It means that, well, here almost 50% of our heap is free, it's not used. Well, but if our application will decide to allocate the large object, well, there is no continuous space for the object, so we are, bad luck, we need to solve it somehow. And the solution is usually expensive. From the other hand, if our garbage collector is doing, is doing compactation, well, after the end of the GC cycle, we will end up with the heap looking like this. So all living objects will be grouped together, and we will get continuous free space. So now, if application decides to allocate a large object, well, no problem. Here is the space. So that's a different. So from this, it means, well, we always want to have a compacting GC. But as I already said, there is no such thing as a free lunch, so the compactation has its costs. So now we know three basic terms which are, parallelism or parallel GC, what is parallel GC, what is concurrent GC, and what is compacting or non-compacting GC. So we can look at the JVM, what the JVM is offering for us. So in the first category, well, or the first group, in the first group there are two GCs. First one is called serial GC, second is called parallel GC. Well, what they have in common? They are not concurrent. It means when either of this is running, your application is not. So once either serial or parallel GC kicks in, your application is not doing any work. Difference between them is that a serial GC is running in one thread. It means it's not in parallel, and of course, parallel GC is running in multiple threads. There are different implementation of these collectors for young generation space and old generation. That's not important now. What is more important is that memory is cheap. And when the memory is cheap, we would like to, well, use more memory. And more memory means bigger work for our GC. Our GC needs to do more work to reclaim the larger area of memory. And because these two GCs are not concurrent, well, and they need to reclaim or to reclaim more memory, well, they will run longer, and longer they run, longer our application is paused because it's not responding, as we could see in previous slides. So there it's usually not big issue. Don't quote me, sometimes it is big issue, as long as your heaps are reasonably low to few gigs. Of course, it depends on your use case, but bigger heap you have, well, the bigger poses you will have, and at certain point the poses will happen to be unacceptable for you, and you need to look for a solution. Well, the solution is, of course, concurrency. If we have a bigger pose, we really want to be able to reclaim unused objects concurrently, and so the application will be still running. And we have two implementations in JVM. The first one is CMS, concurrent mark and sweep, and the second one, which is the topic of this talk, is a G1. G1 is quite new. First time it was in Java 6 update 14, and officially it's supported from Java 7 update 4. So as you can see, it's really quite new, and we will see later it has the consequences. Well, before we dive into G1, first look at how CMS works. And as we said, our heap is divided into two areas, old generation and young generations, and we have different algorithms for it. So first look at how CMS usually works for young generation. Well, we already said that all objects, almost all objects, there are some exceptions, but almost all objects are allocated in a young space. And this young space is divided into, well, three areas. First one is hidden, when all objects are allocated, and two spaces called survivor. We will see what is it good for later. So our objects are allocated in hidden, and well, the hidden is slowly growing. And when hidden is full, well, the young GC will kick in, will collect the garbage, and the objects which are still in use will be moved to one of the survivor region. So after the end of the young GC cycle, we will end up with empty hidden and with some utilization of one of the survivor region, and the second survivor region will be empty. So it will look like this. And, well, the application is continuing to run, and again it's allocating objects in hidden, and again the hidden is growing. Once hidden is full, again young GC will kick in and will again collect the garbage. It means unused objects from hidden. Unused means objects which are not referenced from anywhere, and will move them to second survivor region, and it will do the same for the objects in the first survivor region. So we will end up in a state like this. Again, after young GC, we have empty hidden. That's important to remember. After young GC, we always have empty hidden. We have empty one of the survivor regions, and we have some objects in the second survivor region, so on and so forth. And, well, we can see that the objects are being copied between two survivors. And once garbage collector will decide that, well, this object is no longer young, it can be considered old or tenured, it will copy the object into the old area. So this is the idea how CMS works in young generation. What is important, all the young GCs are stop the word. It means it's not concurrent, it's not running concurrently with our application, but given that the young regions in heap are usually small, well, most often it is not issue. Sometimes it is, but the idea is that the young generation will be small, so this will not be a big issue. And the second idea here is that, as you can see, the heap is divided like physically, like the area allocated for young generation is continuous, and the same is for old generation. So there wasn't much specific CMS-specific things here. There are some maintenance background task for CMS in Young, but that's not important. Important is it was stop the word and heap is divided physically. Well, how it works, CMS in old generation, it's a little bit more interesting. We can divide CMS in old generation into 4 main phases. Actually, there are more phases than 4, but these 4 are the most important. First one is called initial mark, and in this phase it is stop the word. It means it's not concurrent, despite the name CMS. It's not concurrent phase. So when this phase will kicks in, well, your application is not running, and the garbage collector will mark so-called root objects. Root objects are objects which are referenced from thread stack, from young space, and so on. This is stop the word. That's bad news. Good news, it is usually short, so the stop the word is a short, and usually you can tolerate it. There is a second phase which is concurrent. It means it's running together or concurrently with your application, and during this phase the CMS is following the roots from the initial marks and is, let's say, creating a graph of a living object. So it means that after the end of this phase, CMS will have a map of all objects, or will know which objects are still alive, or almost all, because there is the third phase called remark, which is again stop the word, and what the remark is doing, that it is trying to find changes in which were made during a concurrent mark, because remember, concurrent mark is running together with your application, so there might be some changes. So remark will stop your applications, will stop your threads, and well, will look what has changed in between. And there is a third phase, which is called concurrent sweep, and that's the phase when the objects will be actually reclaimed. So this is CMS in old generation in a nutshell. It's very high level, yeah. So the point is not to give you an idea how it is implemented, but the point is to give you an idea about the principles behind. So important to remember to stop the word pauses, concurrent marking, and concurrent sweeping. Features. Most important feature is that it is not compacting. So you will end up with a fragmented heap, which, if you remember, will look like this. So this is what might happen when you are running CMS under under the some loads, under some specific loads. CMS is actually trying to be clever about this, and it's trying to avoid fragmentation by using different lists of free regions, according to size and so on and so forth. But sooner or later, you will end up with fragmented heap. And what does it mean, fragmented heap? Well, as I said before, you need to solve it somehow. You need to defragment it, and well, our defragmentation of our memory is a serial thing, and it's stop the world. So if you end up with this, and you need to allocate you need to move a large object to your fragmented heap. Well, yeah, in your logs, you will see something like promotion failure. There is no space, continuous space large enough to do so. Well, I need to run something called full GC, which is stop the word. It's usually taking a long time. Your application is not running. Your customers are crying, and your boss wants to kill you. So that's not so nice consequence of this. Well, another catch of CMS is the remark phase, which is stop the word, and well, sometimes it can be quite long, and again, the same consequences. Your boss wants to kill you. And even when CMS is well designed for large heaps or to run concurrently with your application, sometimes if you have really large heaps, the poses, most likely the remark phase will be unacceptable for you. My colleague called Matt, well, I asked what is his opinion on CMS, and he said, well, it's working very well except when it's not. And when it's not, it's usually working terribly. So that's things to remember. So stop the word. Stop the word is our enemy. We want to eliminate these pauses. And here comes G1. If you look at the characteristics of G1, you can read that it's concurrent, it's parallel, it's compacting. And I'm saying it's kinda concurrent, it's kinda parallel, and it's kinda compacting. So, because, well, usually when something sounds too good to be true, it's not true. And we will see that, well, yeah, it's concurrent, parallel, compacting, but all kinda. So, before we start to dig into G1, it's good to know what were the design goals or goals when G1 was designed. And probably most important goal was to have a low latency. It means to either not have stop the word at all, or, which is more realistic, is to have as short stop the word pauses as possible. So that's the first and main design goal of G1. So low latency, and low latency even when you have a big heap. Another goal was better predictability. Well, yeah, it's a Java, so you need to accept that there will be some pauses, and well, sometimes they will be shorter, sometimes they will be longer, but well, you really want that these poses to be predictable. So you want to know that, well, the poses, or most of them, will not be longer than, let's say, 300 milliseconds. And, well, maybe you can live with this. And the third goal is, to have a garbage collector which will be easy to tune, which is not the case in CMS. So, how it works? How the heap looks like? Well, it's drastically different from what we saw before. So, all other garbage collectors based on generations in JVM, well, they split the heap into young and old generation, and physically it means here is really some continuous area in memory which is considered to be young generation, and, well, there is another area which is considered to be old, and all these areas are continuous. In G1, it's very different. Instead of having two areas, we will split all heap into regions of equal size, and every region can be considered to be either young or old. So it's more like a logical split. It is not physical. So we can really have layout like this. So there will be some regions will be considered to be young, part of the young generation, some will be considered to be old. It's good to know, or worth mentioning, that the size of each region is between 1 megabyte and 32 megabytes. The size is always power of 2. And yeah, each region can be either young or old. And what is very important, when G1 is collecting the heap, it's collecting by region. It's trying to collect each region separately. So if we happen to have some stop the word poses, well, it will be they will be shorter, because now we are not collecting all the heap but some regions. We will see this later. And what is very important to know, at least for now, that besides these old and young regions, we have something called humongous region, which is some place intended to be used for large objects. Where large objects means objects larger than half of the region size. And, well, in current version of G1, G1 is not optimized to collect this humongous region, so take this in mind. So, how it works? So, we know that now the layout looks like this. So this is our first snapshot. So we have some regions marked as the old, and we have some other regions marked as the young. And, well, when we start to collect the young generation, we will scan all the regions marked as a young. We will find what is still used, and we will move it to previously empty region. So we will end up with something like this. There will be obviously more young region than one. What is important, the regions originally used for young generations are now completely empty. So we will end up with having a continuous space size of at least one region. Important. So we see that now, if we think about it, we can see that, well, probably the fragmentation will not be as big issue as in CMS, because after every cycle we will end up with completely empty region. Also, I forgot to mention that this young GC cycle is stop the word. So, but again, it's young, so it's supposed not to take a long time. And also during this young GC cycle, it will calculate some statistics, to be able to resize young GC for next cycles, because we don't have this physical hard division, so we can say, oh, maybe it would be good to have more young GC. Well, okay, we will use more, so we will use one extra region, so on and so forth. So, how old generation GC works in, well, G1? We can look at this as a combination of CMS and parallel compacting GC, which I didn't mention, but, well, I guess most of you are familiar with parallel GC. It's a throughput GC, if you happen to know under this name. So when I said it's a combination of CMS and parallel, it means that there is a concurrent marking phase. So concurrently, it means together with our application, we will be able to mark what objects are still alive in the heap. The remark phase, if you recall it from the CMS description, is still stop the word, but there is a different algorithm, and it is supposed, and usually it is, to be the remark to be way faster than in case of CMS. And if you remember from CMS, the initial marking is the phase when we are looking for our root objects. Well, it is also stop the word, and currently there is no separate phase as per se now, and it's now, let's say, piggybacking on young GC. So in the logs you will see like, hey, I'm starting young GC and also I'm doing an initial mark. So that's good to know. And also during this concurrent phase, well, we are looking at each region, and we are trying to, or GC is trying to calculate a ratio of living objects in every region. So that's one kind of statistics, and another statistics worth mentioning is it also looking who is from the other region is referencing objects in our region. So we will end up with two basic statistics. First one is ratio of living objects, so it means the ratio between objects which are still referenced and between non-reference objects. And also we will end up with information who is referencing us from the other regions. So once we know what's the ratio of living objects, and if we are lucky that we will find out a region where are no live objects, we can immediately reclaim the region. We can say, well, no one is living there, so there are no living objects, so well this space is free to use, and well, it was quite fast, so that's great news. But obviously this is possible only for regions there are no living objects, which is not really very often. The more often case is, well, you will end up with information which objects, or which regions have least living objects, so which are worth to garbage collecting. So you will end up with information that in this region, are the objects are mostly not referenced. So during the next GC cycle we can collect these regions, and again it's similar as in young GC. We will end up with something like this. So the regions which were marked for collecting are now empty, and the one region which was previously empty is now in use. What is again important to know that there is no separate GC cycle for all generations. So when it is always doing collecting of young and old together, or it's collecting only young generation. So in the logs you can see something like this: GC pose mixed. It means it was collecting mixed between old and young generations. Previously, in previous version of G1, this was not called mixed, it was called partial. So during the old, or for collecting the old generation, well, we calculate livingness ratio of each region, and we will find out based on this and other informations which regions are the best to determine, evacuate, to collect, to move. And the best are, well, the regions which have the best ratio between the work and the result. And yeah, another important is we happen to find out region without living objects, we can reclaim them immediately. There is one term which is good to know when playing with G1, and it is the term remember set, which is a structure intended to track references between regions. So we have for each region we have one remember set where we are tracking the references from the other regions. It will allow us to find references to objects in our region without tracking the full heap, so we will save time. And so far we know quite a little about GC, but we know that, well, there is some structure, this remember set, which is tracking the references between regions, and well, if we happen to have large remember set, it means a lot of dependencies or references between objects in different regions. Well, probably not very good idea to use G1, because we will end up with large result set which will be expensive to maintain. And during GC we can even end up, if result set is larger than some threshold, we will end up in full GC. Stop the word. So from this we can see that probably G1 is not a very good collector when we have some complex graph of references between objects, because, well, more complex graph it is, well, the larger remember set. So take this in mind. And also, second gotcha is, well, as I said, there is this humongous region which is currently very expensive to collect. So if your use case is to create a lot of large objects, well, again, probably it's not a good idea to use G1. I promise that we will look a bit at the tuning. Okay, well, before we start to tune at all, should we make a pause or? Okay, we are running out of time, which is a bit pity, so I will try to be as fast as possible. Now? Okay.
So we have a massive queue, we need to finish quickly, very, very quickly.
Okay. Well, I've been told that we need to finish quickly, which is a shame because we have quite a lot to go through yet. Well, for now, important to remember, G1 was designed to have low latencies. So use it only if latency is your goal and you have you need a large heap. So if your goal is a throughput, do not use a G1. And well, another very important thing is that it's very easy to tune, or it's designed to be easy to tune. So most important option is max GC post millis, when you can specify what should be your maximum post time, and G1 will try its best to fulfill this, but it's not a hard promise, it's just on best effort. So I have one small slide I want to go through, this one. So, no. Okay, so well, the message is I cannot recommend to use G1 in production as yet for as a first option, first variant. Always use it as a last effort when you end up with all other variants and everything else is failing, because well, it's still quite new. So I'm sorry for having to cut this off, but well, that's the end.